So before we get into this presentation, I think it's worth mentioning two things. One is, so just when I was having lunch with somebody, when I shared the table with somebody, so we introduced each other, and she asked, like, okay, why are you here for? Then I said, okay, we are working on TizenRT, so and so. So she asked, like, okay, so TizenRT was introduced in 2016, and you are here in 2019, and the title says it's a reliable platform. So does it mean that till 2018 it wasn't reliable? No, not at all, okay? So we have added more features to make it reliable. So what are those is we are going to discuss about. Number one. Number two, worth mentioning is, so I clearly mentioned that this session needs a background on real-time operating system concepts and a little bit exposure to the embedded development. So I assume that you have a little bit of background. Even otherwise, it's OK. Thanks for being here, OK? And let's get in. So hang on with me for the next 30 minutes. Initially, I had a totally different set of slides. Then after knowing the session timing, that it is after the meal, 2:30, I cut a lot of text, cut down my speech, and introduced a couple of video demos to make it as interesting as possible and make it difficult for you to take a nap, OK? Perfect. So, OK, we can skip this. So what was the motivation for this work? So TizenRT, as I said, it has been reliable. The reason why I say it has been reliable since its inception is that it has been already deployed commercially since 2016 and even in 17 and 18 in, if not millions, but at least hundreds and thousands of consumer appliances. Okay? So that speaks for the reliability. But what was the motivation for this particular feature or enhancement is this. First, crashes. There is no platform without crash or issue, okay, as long as it's a software. Number two, it's developed. There are multi-party stakes. So there are hardware vendors who give the firmware. We develop the TizenRT real-time operating system and framework. And there are third-party developers and the app developers. So it's very important whenever there's an issue or something happens, it's very important to converge on the root cause as quick as possible. Okay? Number three, proximity to devices, which is just very difficult because once it's deployed commercially, it's very difficult to have a physical access to those devices if there is a problem. Okay? So the ideal solution would have been, if not eliminate the crash, try to mitigate it. And whenever there's an issue, make it easy to converge on the root cause as quick as possible. And third one is do everything on the remote. If you don't have access to that, try to do it on the remote. Okay? That's how we have been trying to do. So just a brief evolution of TizenRT towards reliability, just 2 slides before we jump into the details. First, so this is how it was introduced in 2016. So how many of you have heard of TizenRT before? Perfect. OK, great. OK. So anybody is using or developing OK. So this is how it was introduced in 2016. It supported just one flat build. Okay? There was no clear kernel versus memory space separation. And then you can see in 2017, we introduced this protected build. And so where we split the kernel and memory space, so to add more protection. And then the binary gets split into kernel binary and user binary. And this is where we are now in. So here, not just the kernel and user space separation, but the user space is split into multiple, or each application is restricted only to its user space. So you will get to know more details, because this is what I'm going to talk all through that. So I hope all of you have at least exposure to any one of the architecture, like ARM or Blackfen, MIPS, anything, okay? Because it's going to be a little bit of exposure to hardware will be very helpful, okay? So continuing continuing from that, so why we did this? First, image and recovery system. First, in this build, it's one single image, and it's a fixed position code, okay? So once you build, and the code is fixed for that particular location of the memory, it cannot be moved across. That's how it was. And application can access, so there's no kernel user separation, so all accessible to all. And then this, in the second protected build in 2017 or 18, so again, it's a fixed position code, but there's a protection between user and kernel space. So what we are here is multiple, so it gives the flexibility to the application developer to make their own application as a single binary, which can be updated live, okay, whenever there's an issue. And it also restricts each application from accessing the other application's memory space. Now, if you are from a luxurious ARM architecture like A series, which has a MMU, then you might think that, no, what is the point? Why do we have to access? Because it has a virtual memory, so by default, it has this ability. But TizenRT is mainly emphasized or focused for microcontrollers, okay? So for like M and R series, it does not have an MMU. That's where it makes sense to isolate, prevent an application from accessing other applications' memory space, okay? So advantage of doing this is if there's a fault in the user app, then yes, that particular binary alone can be restarted or even updated, fixed and updated live from the remote, okay? So now, as I said, to cut my speech, you know that a picture is worth 1,000 words, but a video is worth more. So instead of me talking a lot, I thought, okay, let's make a demonstration. It would have been nice if you can set up the real demonstration of this, like how it is deployed commercially. But because of logistics, we couldn't do that. But I have made a demonstration with simple applications, and it's a recorded demo, okay? But before getting into that, what it has, okay? It's just an illustration of how it behaves. There are two applications, okay? One is a running counter application. All it does is every 2 seconds, it just increments the counter and prints it, okay? Second one is a rogue application. As the name says, it just randomly writes or reads from any of the memory space available in the CPU. Let's see what happens, okay? So it's self-explanatory. I don't have to. But unfortunately, I couldn't pause and control as it goes. So you can see it's loaded, okay? The rogue application is loaded, and the counter application is loaded. You can see the counter application, every 2 seconds, it's just incrementing and printing the running counter value. And the rogue application says, okay, I'm good. All it's running. Okay, now it speaks your mind. It says it's boring. Now it says, okay, I'm going to perform a memory write outside my memory space randomly in 15 seconds. So this is what happens when, so after this it's paused, okay, because I have intentionally paused it. It's animated pause. So in real world, when application vendors or all this develop their own code, and there is no guarantee that all the code is clean and perfect. So something will overwrite some other thing, or it might even overwrite its own data, so which corrupts it. So when that happens, okay, that's a crash. Okay, now at the end of the crash, you can observe two things. Number one, the rogue application is reloaded, okay? Number two, the counter application is not disturbed at all. This is what we want, actually. We do not want any one of the rogue application to bring the entire system down. Got it? So now this would have been very simple if you are using a hardware with the MMU, because it can never happen. But when you don't have a hardware with the MMU, how to emulate this, how to do this is what we are going to talk about. So how was that achieved? Okay, first, okay, just for the next 3 slides, this is where I said it's important to have knowledge about any one of the architecture. So how each binary or each user application binary is built is, so the platform libraries, the kernel are built, and from the libraries, so the corresponding user space application source files are compiled, and those object files, while linking against these libraries, the symbols, which are all used by these applications. When I say symbols, the easier term to understand is APIs. So those are copied. It is not partial linking. It's fully linked. Okay, you can see the address, fully absolute linking. That means, so another user application which uses the same symbol will have its own copy. So there can be symbol duplication on each user binary. Okay, but why? And the reason is we do not want to share any of the symbols or memory space across user binaries. Okay, so this is how it is built. So, and it is, as I said, it's a absolute linking, and so the start address is 0, and from there it starts, and the binary is built. Second, how is it loaded? So whenever you want to load a binary, you need a loader, very simple. So yes, there's a loader, okay? And here comes the difficult part. So you have when you want to separate or isolate the one user binary space from other one, it should be contiguous, okay? Contiguous, and it should be completely separate from other applications. So what we did is, okay, there should be a real estimate of the runtime heap and runtime stack size. Okay, you set it as a configuration values. So if the binary size is 1K, and if this is 2K and 2K, so 5K memory space, contiguous memory space on the RAM, internal RAM is allotted, and it is loaded. Clear? Okay, now how is it executed? So we introduced this new manager called binary manager and loader, because we need loader to load. So at the init service, whenever the kernel inits, it launches the binary. So these all runs in the kernel space, and the application runs, the binary runs in the user space. User space application runs in the user space. So the loader loads and executes, and the binary notifies the status, whether it is successfully loaded or not, back to the binary manager. So it's very simple, like any normal loading and execution, okay? This is all. This is the crux of the entire enhancement. That's it. This one slide speaks everything. As I said, so these Cortex-M and R series don't have MMU. Instead, they have MPU. Yeah? So how many of you know about MPU, protection unit, memory protection unit? Okay, great. So if not, it's just a hardware unit. Whatever the value you populate with, and whatever the attribute you set to that, if you say like from 1,000 to 3,000, I want to be readable or writable, then those memory range alone will be allowed by the hardware to be modified. That's it. It's a hardware unit which gives you this ability to restrict. Okay. So let's walk through how this works. First, program counter, PC stands for program counter. If the execution is in the kernel mode, okay, it's in the kernel, if you see the MPU configuration table, it's completely empty. That means if the execution is in the kernel, it can read and write, modify anything anywhere inside the processor memory space. Okay? Next, it jumps into the execution into the binary space, binary A space, okay? So binary A has, as I said, the code which is loaded. This code region is the one which will be loaded, and the data is the configured value. This is one contiguous memory region for binary A, or the user space application A, okay? When the execution jumps here, you can see, so from start address, for the next 0x512 size, the attribute is set as executable. So once this is set, then execution from this range is allowed, but still it is not allowed to read and write. Whereas, see the next one, 0x4512, for the next 0x256 size, the attribute is set as read and write. So this is the data. So if the execution is here, all that binary can write is this range and execute is this range. The moment it crosses the boundary, that's it. That's what you saw, the crash and data abort. And all other applications can still continue and run. Okay? Now the execution jumps into binary B. So you can see dynamically the MPU configuration tables are updated. So now this allows read and write for its code range and execution for, read and write for its data range and execute for its code range. Okay? That's simple, that's it. Okay, why this slide is important is now, okay, now we have restricted one user space application from other, so how do they communicate then? That's when this IPCs comes in, inter-process communication. So TizenRT provides a large set of IPC. One is message queue, signals. We'll come to this fast IPC later. This is very recently we introduced only in TizenRT. Socket pipes, these are all common. So how does this work when you restrict one user application to other one? So all it has to do is if binary A has to talk to binary B, or user app B wants to talk to user app A, then it has to send the data. When the execution is here, it has to send the data to kernel, and kernel will, then the execution moves into kernel, then from the kernel it writes it into the binary space A. Because if in the kernel mode, the entire range is accessible for the kernel. Okay? But the fast IPC will come back to that at the end. Okay. So now, we did this, and what are the real benefits? Okay. First, as I said, the ultimate goal was to, if not to eliminate, at least try to mitigate the crash, number one, and prevent error propagation. Because if you restrict the error from propagating from one application to another application and make it more ambiguous for debugging, so now it is prevented. The propagation any error in one application is restricted to it. Then remote update, we will see that. And fault handling, because whenever a user app falls, either it can be fixed and updated on live. That is possible now. Then diagnostics. So any crime of act, if it is caught at the time of action, you get the most details. So right now, when the user app crosses the boundary, it will create a fault. And in the fault handler, you can get the entire backtrace. What is the reason, who is crossing the boundary, which process, everything. As I said, this gives the flexibility to converge as soon as possible on the root cause. Okay? So the live update and fault handling, I don't know, so since few of you don't have the operating system background or hardware background, I'm not going to get too much into this. But what it does is, how a live update can happen, because when a processor falls or fails, first it will notify to the binary manager, okay? So binary manager can do two things. Either it can check if there is an update available, or it can restart the application, try if it works again, okay? So it tries 2 times, 3 times, and if it still continues, then that's it, it'll stop. How it handles, you'll see the next slide, but it will stop reloading at that, and if there's an update, it will use that. Otherwise, it will not update, it will neither update nor reload the same application again. That's what the right side is. But the left side is, so let's say that there's no issue or anything, but you want to change the version of a user application because you have added a new feature, you want to just update the version. In that case, TizenRT has a photo client, which stands for firmware on the air update client. So there's a server, which is the photo is completely outside the scope of this presentation, but what is the purpose of that is to aid in firmware update, okay? So the photo client will notify binary manager, hey, just update binary 1, okay? So then binary manager will take it forward to loader, and loader will decide, okay, what is the version that's currently running, and what is the version that is available in the server? Do I need to update? If there's a need to update, first it will notify to the running task or the user app, hey, I'm going to update you, are you ready? And it waits for it. Once it gets a confirmation that the task which has to be, the user application which has to be updated is ready, then it notifies to all other applications or binaries, are you using this guy? I'm going to update this guy, get yourself ready, okay? Once all that is done, the loader unloads the binary, unloads the user application, then downloads the latest version from the server and runs it and executes it, okay? But if you want to know the code details, it's always there in GitHub. You can just search Samsung/TizenRT, you'll get it there. So, oops, okay. So diagnostics. As I said, when user of B tries to access A directly, and it creates a fault, and you can see here. So this is the dump, and you can get all the details, okay? So the register values, which application is trying to, what is the process ID, and what is the backtrace, and you will get the call trace, so you will know where the problem is, okay? And this is the second part. The first one we saw that it crashed, but it just updated here. You will see a live update. That's version 2, like whenever there's an update available, how it updates. So it's all the same, but I don't have access to run it forward. Okay, now it's going to perform an operation outside its memory space. Okay, if you see here, okay, so this is it. So this is the updated version, and you can see the version number here and a different set of logs. So it clearly says, okay, this time I'm not going to try an adventure. I'm not going to write outside the memory space. Okay, got it? So it crashed. Since there is a later version available in the server, it just pulled the latest version and it runs. So in the commercially deployed environment, this is very useful, very helpful, and it has cut down a lot of man hours debugging the customer issues. Okay. So now, what are all the modules we introduced or changed during this? So in the kernel, so we brought in a ELF loader and the fault isolator, the changes, and we introduced the binary manager and the MPU. Okay? And in the user space, because each user space application has to be given a separate memory range, the memory manager, user memory manager has been modified a bit. And this is the FOTA service, over the air service changes. And this is the corresponding user space module corresponding to the binary manager in the kernel space. Okay, so what are the challenges and pros and cons? Okay, the first challenge, first we'll see the challenge. The main challenge here is estimating the runtime stack and heap usage of a binary or a user application even before. That is one challenge, which right now they are just giving an extra space and make sure that it has enough memory. And pros, yeah, you can now perform a live fix and update. You can mitigate memory corruption, and it gives the diagnostics on the time of act diagnostics. And so what happens in the commercially deployed is, in the commercially deployed environment is, whenever there is a crash, the binary manager collects the diagnostics and it dumps the diagnostics into the user space memory, and it can even notify the user space application this diagnostics is available in the user space, so that application can take it and use it as they like it. Okay, and increase system stability. Okay, this one is very important now because we work with multiple vendors, hardware vendors, third-party developers. So now this prevents ability to build the user application as a separate binary by themselves, prevents one app developers waiting for the other one. They can just, once the kernel is built, once they get the kernel, they can build their own user binary and they can just deploy. They don't have to wait. There is no dependency between each user space application. Okay, but what are the cons? First one, symbol duplication, I said. So the memory size is going to be big. So because you are going to copy whatever the symbols you are going to use from the library, you're going to copy it in it. So it's going to be multiple instances of the same symbol across user binary. And context switch overhead. Whenever a task switch happens from one application to another, there's going to be an overhead. The reason is this guy. Every app switch, context switch, dynamically this MPU table has to be updated. This doesn't come for free, okay? So now, when we looked into after doing all this, when we looked into the performance and when we checked the overhead, we found there's a considerable overhead. Then we figured out, okay, then we tried to see where does this come from. One is this MPU configuration changes. Number two is the flash file system. Sorry, the flash. We are right now loading from the flash, so which runs with the MTD. It has a very low latency, and that adds an overhead. And the third one is IPC. So you see here, it has to copy from one application to kernel, so it's like a dual copy. Okay, so we made a little bit of effort to address these three. So first, for the flash, we are trying to load it from the file system. Okay, and second, for the MPU, what we are trying to do is, so instead of updating this as two separate attributes to mitigate this, what we can do is, for this entire range, we can just set it as read and write. Read, write, and execute, so that the particular application can do whatever it wants within its memory space. So this will cut this as one single entry. So updating one single entry in MPU takes very less time than two entries. That's the second effort. Third effort is, okay, so to cut down this dual copy, that's when we introduce this fast IPC. So how does this fast IPC works is, let's say that you want to transfer 10 bytes from, 100 bytes from B to A. So the address of this is passed to the kernel, just the address, not the full data. And the source and destination address is passed, and then the context is switched from user to kernel, because if the execution is in the kernel can copy from anywhere to anywhere. So all it has to know is the source and destination address. Instead of copying from here to here and writing back, what you are trying to do is, but it's not a fully tested, but this is what you are trying to do now. I think that's pretty much, that's the end of it. Thanks for staying awake, and if you have any questions.
Yeah. What kind of hardware can we put this real-time operating system on? So are these boards we can just get?
So
are these simple boards we can get somewhere?
What we are right now, open source available boards are IMX, NXP boards. So IMX RT 1020 and 1050 are the public boards which are available. You can just use, and all this will work.
Is this available as documentation somewhere?
Yes, on GitHub. So you just go to the GitHub and Samsung TizenRT project. You can see the README and documentation, everything is available.
I wanted to ask about the fast IPC.
Okay.
Is it like the memory is being shared between the two processes when the address is passed, or the kernel is going to perform the memory copy?
Kernel is going to copy from the source and write it into the destination.
Okay, it's not like the address.
No, it is not the shared memory.
It's not a shared
memory. No.
Okay.
Okay, all good. Thanks for joining.